never fear, I'll be using the board. But what we were speaking about last time was this idea of taking polymer chains and networking them, forming some kind of structure. And importantly, as Mark also emphasized in his first lecture, is that we turn things that look like shoelaces or single molecules, and somehow by turning them into networks, they become volume-filling structures, certainly, so something that is a three-dimensional structure. We discussed last time that there's a certain type of randomness in how they assemble, which we need to take account of when we perform calculations or want to predict or understand the mechanical properties of such systems. And related to that is really a set of ideas of how do you transition from a bunch of single molecules to something that is a network. So here we have an object made of some kind of rubber. So it certainly has some kind of properties where it's certainly not a liquid, it's not flowing out of my hand, which would be a property of the individual molecules. So one can ask you, what is the characterization of the phase transition of turning something from a liquid of polymer chains into an object that's not like metal or something like that. It's not crystalline, but certainly can resist my pulling on it and doesn't flow exactly like a fluid. We have the idea of a phase transition that also occurs there. By the way, these are not necessarily all questions that have been completely answered by now, so there are so many challenges for the younger generation, such as you, to answer about. Okay. You also saw great nice pictures about where things occur, so I'll just show this again. Naturally, inside cells, you might get network-like structures that form backbones of the mechanical integrity of the cells. But let's visit rather my more comfortable territory, the theorist's position of this, and let us remind you of what we were looking at last time. So last time we were taking individual polymer molecules and we were thinking about stretching them. We recall that they behaved like springs, and that the spring coefficient of one of these springs depends on how many such bonds there are, and it also depends on the temperature. And we were thinking about the simplified version of my real-life experiment of stretching this object as just stretching these springs. So what you saw in that little cartoon over here was my pulling these walls apart and just simply thinking about how does the force change when you change the distance between the ends of these springs. So a very standard polymer physics question. And you can relate this to the fact that what happens if I connect these two springs, how does that make a difference? So we spoke about the connecting of these two springs as forming some kind of cross-link, and that this is some constraint on the system, and clearly it modifies in some or other way the way in which these objects fluctuate. So let's compare the simple pictures again. So we have, and this is going to run or not, we have individually fluctuating molecules, and you're just changing the positions of the ends. Then you go, and as you move the walls apart, then you go to the second scenario, and now they are coupled to each other, so the problem has become a lot more complicated than just simply two coupled springs to each other. Of course, with a network, we have to imagine that the situation is repeated many, many times, and in a far more complicated scenario than depicted over here. But I hope it just reminds you of the mathematical complexity or the conceptual things that you have to think about. As soon as you produce a network, you're connecting things, and everything becomes connected in some other way. Okay, so we can play these games a little bit more. We can remove the walls and think about not the walls there, but these points as being connected to the rest of some kind of networks. I just believe that we're zooming into some aspects here. So, what was the idea? The idea is that you might have polymer chains, and if you are good here, you put sulfur, indicated here by a two blue sphere, in between this, and it sticks two chains together in a way that is permanent, coupling their fluctuations. This is what we call a crosslink. And last time we also introduced the idea of the functionality of a network. Remember what the functionality was? That's seeing how many different bits of strands enter one of these crosslinks. So in this case, functionality of such a crosslink would be 4, because there's 1, 2, 3, 4, and 4 bits of strand connecting. You can think about other chemical scenarios where you can have 3 strands connected at a point, or 6 strands connected at a point, and clearly they play a role in the eventual elasticity such a network might have. You can think about a scenario where you make this a little bit more complicated. Here is a hugely complicated crosslink. There's lots of little strands, little hands that can attach to polymer chains, such as this, and then other polymer chains might connect to this at other bits, and we can have rather complicated network structures. You can think about multifunctional linking, so here you have polymer strands, sometimes they are cross-linkers with 2 hands connecting 2 bits of a chain, making it tetrafunctional. There might be others with 3 hands, increasing that cross-linking density, and you can think about mixtures of these kinds of things. So I don't really want to go into that. You can think about an example, and we heard about and saw these particles in another context last week, the so-called Young's particles, that have different regions that can cluster together and form different types of crosslinks. And then you can, for example, write a theory and say, when does such a network form? When is the network just some kind of collapsed blob without properties? And you can figure out how many of these different types of crosslinks there are. These are just some of the physics questions that one might ask about such polymer networks. What are other questions you can ask? You can think about cross-linking a system, this is rather poorly visible, in some kind of confined regime. And you can say it links to the walls of a cell and to each other. And then you can figure out, how, as you change the affinity of the different types of cross-linking, does the profile of cross-linking in such a confined geometry change? But more importantly, here's what we have. We have molecules swimming around, changing their position with time, some kind of horrible fluid. Okay. Horrible in the sense that perhaps the maths is not so easy. And so what you would want to do is you take a snapshot of the fluid, you do a Goodyear story, and you introduce crosslinks over here. Okay. So all at once, these molecules are not necessarily all independent. You then have a sample of this fluid. The molecules are swimming around inside a certain object. You think about deforming it. And if it's just a fluid, then of course you have a completely different response than if you were to cross-link this and then change its shape. So we're interested in this basic set of ideas, as we've already emphasized, the mechanical properties of such a network, and need to try, or want to try to understand this. Let's introduce a few concepts and go to the board. This morning we already saw the picture that we have some cartoon of the polymer chain connected to something else, perhaps the rest of the network, at a certain point. And then we want to describe its conformation. And by doing, we do that by, we saw this morning that we did this by writing down a vector r, which indicates the position of a certain part of the chain in the space in which it moves. Where we introduced S, or where Greg introduced S as the arc length along the chain. So we have different measures of trying to explain what we have. We need to see how many monomers we've progressed along the chain. Say this is the 26th monomer of the chain, described by S, and its position in space, given by the vector r. Okay. And eventually, we want to, when we do the statistical physics of such a system, as we looked at last week, we want to calculate, for example, something like a partition function system, some kind of heat bath. And so what we need to do is we need to sum over all of the configurations of the chains. So we need to sum over all possible ways, all possible shapes the polymer chain can have, and write down the appropriate Boltzmann weight associated with the specific configuration of the chain. That's our basic statistical physical challenge when describing anything with polymers in them. We need to figure out what all of the accessible states of the chains are, and we should in principle be able to do the mathematics to sum over all of these Boltzmann weights. And this is also where the essential difference comes in. If we, for example, take a pink chain and cross-link it here, that the statistical physics of these, of the two independent chains and of the two coupled chains are quite different. Okay, so let's figure out a very simple way in which we can do that, making use of the ideas of the annealed and the quenched averages that we had last. So, if we label this chain by 1 and the other chain by 2, we can write down, for example, the partition function for the first chain if we forget about the second chain. In a similar way, we can write down the partition function and calculate associated properties for our second chain. Also has Boltzmann weight associated with it. How does the partition function for this combined and cross-linked system going to look? Okay. So the cross-linked system consists of both chains. So we need to sum over the configurations associated with the first chain, and we need to sum over all of the configurations associated with the second chain. We need to write down the Boltzmann weight for the chains, whatever that is. We'll discuss that in a moment. For both of the chains. But that can't be it, because I haven't put in the cross-link. So, any suggestions of how one would want to put in, for example, that single cross-link, mathematically at least, such a system? How would I calculate the correct partition function? Any ideas? Let me check who's on Facebook. So, what would you do mathematically in order to put in such an object as that cross-link?
Oh, you have to restrict the motions.
You have to put in, the cross-link provides a constraint. Yes, it connects one bit of a chain to another bit. How would you put in a, well, what is one of the ways in which you can put in a constraint? There's a good old friend or enemy, the Dirac delta function. Okay. For example, this is mathematically to enforce that something has to be equal to something else. What has to be equal to what? If you have a cross-link.
R1 at that point has to be equal to R2.
Exactly. So what you would say is R1 at the point where the crosslink is. Let's call it S star on 1. Okay? Has to be equal to R2 at wherever the equivalent position on the arc length of the other chain is. Let's call it star S2. So that's really the kind of simplest version of this game that we are playing would have to be. So our cross-linked system immediately contains something like this. You can see mathematically how this in principle can make life a lot more difficult, whereas one might be able to calculate this depending on what model of the chain one has. Well, if you use the semi-flexible polymers from this morning, it's doable, but it's a lot more difficult than if you use the completely flexible polymers that we started discussing last week. You have this constraint, it has to move. And it actually means something quite important. It says that these two positions are the same, but it doesn't say anything about the absolute position. So the cross-link's position can, of course, fluctuate. It has to fluctuate in the same way for both the pink and the white chain. Given our discussion last week about quenched and annealed disorder, what kind of situation would you call this, the crosslink in there? Quenched or annealed? Annealed? Who says annealed? Nobody. Who says quenched? Okay, 2.
So what's it?
So it's annealed. It's a superposition. This is all. We all know that quantum mechanics is the right way to do it. So it must be a superposition. We spoke about the two types of disorder and how they play a role in our, could potentially play a role in our cross-linking, and how we need to be careful about knowing what the disorder is or what type of disorder we are referring to when we calculate a statistical physical average. Now, quenched referred to the scenario when we, in some or other random way, fixed the disorder in the system. So the system has no choice but to maintain a specific constraint. Okay. That would be the quenched disorder, and so correspond to the situation where Goodyear added sulfur to his natural latex system. He permanently cross-linked chains together, so once the cross-links are there, they, at least for the foreseeable future, or realistic kind of long-term time span, remain fixed. Whereas in an annealed situation, the system is able to perhaps unlock or shift or change the kind of crossing. So if this constraint, that one bit of one polymer is connected to another bit of a polymer, remains fixed during the duration where we want to calculate things such as the free energy or the elastic response of our system, then this would represent a quench disorder. So our crosslinks need to be not treated that way. So let's think of another scenario, and this is actually a realistic one. Where you say there's a little kind of loop which connects these two. So the crosslink says that these two chains are mutually constrained, but actually the position where it is along the arc length over here, and perhaps also where it is on the arc length over here, so it's like a little ring that connects these two, can shift. So S1 star and S2 star are no longer permanent numbers that are fixed at the same formation. This is called the slipping link. Quenched or annealed? Who says quenched? Who says annealed? Who says a superposition? Well, it depends what you're talking about. Certainly this is annealed because the system can choose some things, the position along this, but it's quenched in a way too, because you're saying that the two polymers are always linked to each other by this slipping link. So it depends how you see it. So actually the superposition answer might not necessarily always be the wrong one. Okay? So if you think about switching on and off that connection, then certainly you have different points of view. So you still have a constraint, it depends on how you see it. You have to be quite careful in terms of the averaging. If you move around, that position of moving around is you need to do the annealed average. If you're thinking about, saying, a single crosslink system of two polymer chains in a completely quenched scenario, then the positions S1 and S2 are random, but you need to average over them in a different way. What were these two types of averages? Well, one way, we said we could average over the disorder by taking our average of the partition function and averaging over the disorder in the same way as you would do any other statistical physics average by averaging over the Boltzmann weights, etc. in there, versus needing to average free energy or related quantities or thermodynamic quantities or whatever, averaging those in this scenario. So if the system, if you know that there's going to be a crosslink, and S1 and S2 are the disordered positions of the permanent crosslink, that is the slipping link, you'd have to do this average. If you have a slipping link, and you know that there's one slipping link, then you might want to do this average, depending on how you view the system, of course, what precise the physics is. You'd have to do your disorder average, the average over S1 and S2, using that. So we've got very similar scenarios which might have very different results. Remember last time we played with these ideas of parallel and series springs and how they were connected, and we did a very simple calculation based on Jonathan Sellinger's question of how do the eventual free energies differ. We saw that they really did differ quite fundamentally in their mathematical form, depending on which scenario you viewed. And you can also think about the physics of such a scenario if you were to compare these two situations. If the crosslink position can change, your system will respond far more easily to, for example, one of these tilting deformations, because the crosslink will just slip along and find another nice minimum. Whereas if you thought about the crosslink not as a slipping link but as a permanent crosslink, even though random, you might have completely different free energy associated with that system. Okay. Let's get a little bit more into the details of how one would want to calculate such a partition type of polymer chain. This morning we heard about the semi-flexible polymer chain. I will be speaking about what is the flexible polymer chain, and Greg reminded us in which limit does a semi-flexible or worm-like chain look completely flexible. Can you remember that?
Persistent length much smaller than the length.
Yes, when your chain becomes much longer than the persistence length, so it's completely forgotten that it's stiff on a local scale. And these were the flexible models that were also introduced in a few varieties last week. And in general, we thought about them and we modeled them by elastic springs. So we thought about polymer chain as a bunch of bonded segments that were essentially some kind of ideal spring. Last time I rather naively wrote down some spring coefficient. Spring coefficient, if this is an entropic spring, as was discussed, depends on what? It's proportional what? Temperature. Remember we spoke about entropic springs. What happens when you heat a polymer chain of some kind of idealized polymer? There's a contraction, and we saw that physically this corresponds, or you can in principle understand this in a simple way. I think about the surrounding fluid of the chain, interacting with the chain. So there's kind of proportionality to this. We also did a calculation for this. If we have springs, we started calculating the partition function of coupled springs in series. We said, well, if we have the spring coefficient, there is our Boltzmann factor, whatever T times the spring coefficient. Let's just call it kappa to distinguish from Planck's constant. Boltzmann's constant. And we thought about the two ends of each of these springs. We wrote it down as Gaussian, so a zero equilibrium extension kind of spring. We did the calculation that if we connected it to the next spring, you have something like this, where we describe positions of the different ends of the component spring with such a walk, and we need to integrate over the middle position. And therefore we would find the effective spring coefficient. What we also needed to remember was that there were some normalization coefficients, some coefficients over here, which we needed to take care of so that everything with these Gaussian integrals work quite nicely. Okay. So eventually, of course, if we're describing an object that consists of n such little units, we'd have a string of all of these multiplied Boltzmann weights of small strings multiplied together. We know from the mathematical properties of Gaussian integrals that in this case the resulting integral, the result will also have to be Gaussian. But so if we take the complicated system, well, it's not complicated, the long or many spring system, our partition function should, in principle, apart from some kind of coefficient, depend on the integral of all of the intermediate positions. And you have something like spring coefficient, and you'd sum x1 minus x2 squared plus x2 minus x3 squared, continuing this until you came to the last element of these springs. Each of these springs you assemble something like that. And we'd say the spring coefficient of each of these springs is exactly the same. Now, importantly, what we saw is that these are entropic springs. Kappa itself is proportional to the temperature, so the temperature, once you multiply this out, completely falls out of this specific example, the Boltzmann rate. So we could replace that prefactor by something that looks like 1 over some kind of length scale squared. And all of these Gaussian factors over here. Yes.
Why are we not integrating from x1 to xn?
Oh, sorry, it's still. We were keeping the two ends of our polymer fixed, so we're still thinking about the effective spring. So we have this Gaussian integral, we know that it will be a Gaussian integral, and all I really want to now do is that mapping that we need. So if this is the way I've written it over here is also a one-dimensional version of this problem. We can easily generalize it to 3 dimensions. But so if we remember that we thought about describing a polymer, say a one-dimensional polymer, as the function of its arc length, x best, as you saw this morning. This is of course a continuum description. With a continuous arc length, you have the position as a continuum. Over here, we are now describing the configuration of our polymer by a set of numbers which just describe the positions of all of the ends of all of the springs that make up this object. So the mapping is really quite clear. We just make all of the springs smaller and smaller, add more and more points in here, and hopefully end up with a continuum limit in the appropriate way. So when we think about this R of S, it usually makes sense to chop it up into tiny little discrete pieces when doing the calculation. Okay. So how do you think would the continuum limit of this look? You're taking the difference of 2 adjacent positions and you're squaring it. What would be the mathematical equivalent on this continuum object? So you're taking the position minus the position to the left, for example, of squaring it. What would be its equivalent or a derivative. So we're thinking about what is the derivative with respect to S. You can always write it as some limit of a discrete process, limit epsilon goes to 0, x s plus epsilon minus x of s divided by epsilon. Basic definition. So you could think about this continuum walk as being the limit of taking two adjacent positions divided by the separation of these positions. So quite logically, our continuum limit of this should be some normalization factor depending on this limiting process, some integral over all functions, continuum functions of S, minus something divided by perhaps another length scale squared. The sum over all of these adjacent positions will turn into an integral of S. And you have something like dx ds squared. That's the continuum limit. You have to do the limit correctly in order to understand what these new and different length scales and normalization coefficients are. You can see immediately from this trick that the difference of two adjacent points is proportional to the derivative squared. It's for flexible chain. Of course, it doesn't look that way for the chain that Greg described this morning. And we see that there's no temperature dependence. So mathematically, we can certainly change our partition function into a functional integral over all functions that satisfy the initial and the final conditions, as Jan pointed out, and something that is the sum or the integral over all of the sides and the derivative. So mathematically, this is, well, this is what you would call the Wiener measure. Example 1 for flexible chain. So these objects are very well studied. I think you might have encountered them in some of your quantum mechanics courses or path integration. Is this familiar to any of you? People in mathematics and finance use such kind of objects. In any case, our mathematics can be turned into the mathematics of a continuum object by just thinking about a continuum object which is characterized by path length and its position in space. It's still Gaussian because it has inherited that Gaussianation. It's never gone away, and we can start calculating the partition function. Furthermore, we can calculate the partition function with the constraints of the cross-linking that is in there, treating it as a quenched system so that we have to calculate the averages of the logarithm of the partition function. So this really tells us is some way in which we can deal with the randomness of how one of these networks of polymer strands is connected. In a way, you could think about this as the geometry of the object. What is connected to what, where, and does it form a solid? Now I'd like to ask you the question, how would you, so we've heard a lot and seen some really spectacularly beautiful examples of forming knots in a variety of different scenarios. Okay? How do you think would the situation of a knot occur quite naturally in this scenario? And specifically, the idea of a conserved topology. Any idea? You don't even have to think in quite as complicated terms as we saw it. Yes, one of our polymer strands. Remember, the ends are cross-linked into some kind of network, so you can't move things around arbitrarily. say at the moment of cross-linking, this thing is wiggling around and doing its stuff and who knows what. So it's wiggling around. All at once you do Goodyear story and you cross-link it. Okay. You're stuck with this knot over here, a real knot, object, because you can't sort of move the knot and disentangle it somewhere else, or in most cases you wouldn't be able to do it. So you've got this kind of knot which is inside, which is somehow captured by the cross-linking process in here. So you've caught a real bit of topology inside your network. So the next question we need to ask, is this relevant? Yes or no? Superposition answer. And can we quantify the relevance? And why is that not good enough if you need to include the idea of the topology? So we're going to be describing this, and towards the end of this week, Chris, who's sitting right in the back there, tall guy with blonde hair, will be telling you a scenario of how you need to think about these knots, why the topology is relevant, and various strategies you might adopt in order to deal with this. Okay. So let's ask another question. If this is inside a network, is this knot in here quenched, or do you think it can be annealed away? It's quenched. You probably can't get rid of it. If this polymer chain was swimming around without cross-linking, is the knot as major or the same kind of issue for doing a partition function as in a polymer network? Would you do a quenched calculation for this as a polymer without it being network? Why not?
Can you disentangle?
Yes, I can. There must be some configuration where everything's moved out and because you're free to move the ends. The system will at some stage disentangle it. Where might this still play a role in polymer physics, though, even though the ends are free? Or in which kind of scenario do you think would the knots still play a role? They're not caught up, they're not quenched, so you can't classify them in the same way or necessarily. So why do you think entanglements still play a role in polymers? Sorry? Elasticity, yes. But you're not thinking, let's think about a process that would lead to the elasticity of some fluid of polymers, so it's not a cross-link scenario. How do you think might this still play a role if you just had a fluid, so the ends aren't constrained in some quenched average, the knots aren't quenched, as you explained? They wouldn't play a role in the partition function. Where might this play a role? Sorry?
I would think a case and say diffusion.
Diffusion in the dynamics. Well, equilibrium statistical physics doesn't say anything about time scales over which things happen, but once again, just think about a simple example. Imagine I pull this really tight, okay? If you waited for it in a fluid, for example, to undo the knot, you might have to wait a long time. Imagine now that there are other molecules. So where are other molecules? Here are other molecules. Other molecules with which it's not. This is your polymer fluid. In principle, they are of course free to move, but it's going to take some time for this knot to open and this one to become uncoupled, so you really influence the dynamics of quite a complicated theory. But it's not the dynamics of quenched disorder, it's just some kind of temporal evolution. And a lot of polymer physics is actually occupied with trying to deal with precisely this kind of thing. How slowly does it take for such an entangled fluid to work? Now, when people write down these kinds of polymer networks and they think about entanglements, there's one way in which you could try, for example, to make some kind of effective theory. We heard from Jonathan Selinger about mean field theories or some kind of effective interactions. So he showed us, for example, the Ising model, and he said that the spin sees the average of the magnetic field around it, and that you could replace that and then get rid of some of the mathematical difficulties and figure out something about phase transition. How? Well, this is of course open to suggestions and there's no unique answer. What would be the average effect? If you just thought about it physically and not mathematically, what would be the average effect of being entangled with one's neighbors, either in a network or in a fluid? So what would the entanglement be? Yes.
You reduce the amount of available states for each of the polymers?
You reduce the amount of available states. You'd be a bit more precise about how would you, what happens to the available states? Which states become more likely and which states become less likely? If you have entanglements. This is just an intuitive idea. It's not, we're not expressing it mathematically at this point. So let's generate an entanglement. Okay. This might be a permanent or not so permanent entanglement. So remember, we're describing the fluctuations of this system.
Aren't they essentially like cross-linked?
They are cross-linked, so in a certain sense you could always think about it as a slipping link in some other way. Polymers. You think about it as a slipping link in some other way, and that's indeed one of the models people have used to describe entanglements. It's a good suggestion. Which other way? Think about it. Do you think that, if this is cross-linked, do you think that the sort of mutual states will allow very large fluctuations this way, or do you think they're going to restrict the fluctuations? They're going to restrict the fluctuations. And so one of the ideas that's been around in the physics community, the polymer physics community for a very long time, that the role of these kinds of things is to restrict the fluctuations by confining it more closely to some original path. So I have to figure out what that is in a kind of tube. So it can fluctuate a little bit, but it can't fluctuate very far from this original path. So this is the basis of a variety of tube portions. So I just wanted to bring this connection of the geometry, the quench disorder, the potential that the chains become a little bit more localized as an effect of the topology, the knotted state in these systems. These are very important questions to think about when you've got all kinds of polymer systems that are flowing, but certainly networks you have to take account of it. So let's write down the full glorious partition function of a polymer network consisting of flexible polymer chains. So we have a bunch of polymer chains coefficients over here and an integral over S. So we'll say a first, a second, and a third polymer chain. We can continue this way. These are then cross-linked. So the cross-links are all are, for example, the kinds of possible ways in which you can connect, say, chain I to chain J. We've got some kind of index which says chain J is connected to chain I at the point S star and J. And you have as many constraints as there are crosslinks. You'd have to integrate over all of the chain configurations, so you do some functional integral over all of the chains that are available in the system. Functional integral. So the Boltzmann weight of these chains is something that looks like the Boltzmann weight, which is just the tropic springiness of this. You've got all of these constraints. The disorder are all of these Sij's, so our partition function still depends on all of these. And if we want to calculate anything, we can't do the calculation in principle. Well, there's some people who have actually managed to, but in principle, or in general, we can't do the calculation with S star ij, some arbitrary number, but we need to average over the disorder. This disorder is quenched, so we have to calculate the logarithm of this partition function, which depends on the disorder, and then average this over all of the possible ways of the disorder. Now, the clever solution to how do we choose this disorder, we also mentioned last time, and actually we suggested precisely the right way in which to do it, or one of the ways which seems sensible in doing it. How do we choose the likelihood of which Sij's the system is going to choose? Remember the scenario that we had when Goodyear cross-linked latex? So there was sulfur in there, he baked it for many hours, but let's imagine he was able to do that, as you might be with modern chemical techniques. So our polymers are swimming around, and at one moment you add the crosslinks in there. Where will the crosslinks go? Can you remember that? The crosslinks will go where the chains are probably crossing at that point in time. So if we say in the crosslinks where the chains are crossing at that point in time, then you've got the basis for choosing this distribution of where to put the crosslinks. And that gives us the important consideration for calculating these basic ideas and for dealing with the network. Not only do we need to understand the role and to enforce the constraints mathematically, we also need to figure out how they are distributed themselves. And the simplest scenario is simply to say, well, they're cross-linked where they are touching in any case. So, if you now take a look at these expressions, how would you, with the mathematics on the board, choose the probability of how the chains are crossed? It's taking a look at the second lower board. The lower board. So this is the partition function of polymer chains that are cross-linked. You are forcing them to touch at these positions. Now I'm saying, what is the statistical physical calculation in figuring out what is the likelihood that a bunch of chains will touch at these positions? you understand the two components of this question. So this partition function, as we wrote it down here, expresses the partition function of chains that are constrained to tangent positions A star. Now I want to calculate what is the mathematical expression for the probability that the chains touch at precisely the positions S star ij. It is exactly the same expression. You can view this with some normalization considerations. This is actually the probability that the chains touch these positions. You can view this integral as some average of the uncrossed-link chains of this whole fraction of constraints. So it's actually calculating the probability that the chains touch at these positions. So this turns out to be quite an elegant formulation. It was first described in a rather lengthy and extremely difficult paper to read by Lehman Edwards in 1976. So there seems to be this morning that we are always referring to some papers from just over 30 years ago. Chart was referred to from 1976. Correct chart there. So we're presenting you with very old stuff, but here we go. As one of the ways in which you can think about cross-linking networks. Some of the calculations involved in this are extremely tedious and quite scary. You have to figure out how to calculate the logarithm of the partition function. You have to figure out how to do these kinds of integrals and to deal with the Dirac delta functions. It's all possible, but the basics of the idea, the basics of what we have here is this difference between the quenched and the annealed average, which in one sense you use the annealed idea to calculate the probability that the chains are going to touch, and you're going to use the quenched idea to calculate the average over this disorder. One way of making a network. What happens when you make a network? You're freezing in the geometry, but you're also freezing in the state of knottedness of the network. And if you integrate over all possible paths the polymer can take, you have to be careful, in principle, that there might be some paths that are permitted or that have a weight from this real measure, but that are not permitted by the topology because there is a state where this polymer winds around another one from which it can't escape their configurations. And this is not the same as some configurations such as this. But you see they're quite subtle. They're non-local. You have to deal with them. This is where topology comes in, and that's what Chris will explain to you in a far more aesthetic and appealing way later in this week. That's all I have to say for today. So we're moving towards the more topological issues that emerge from these situations. And hopefully we'll be doing a few more interesting calculations. It's lunchtime. Yes. But before that, it's question time. No questions, so it's lunchtime.